Hi, I'm Stan, and I'll tell you about our work on discrete neural representations for explainable anomaly detection. Anomalies here will be understood as events or objects that have low probability of occurring in a given environment. Examples can include people pushing each other or people fighting. We motivate our work by two requirements that real-life anomaly detection systems must meet. First, they need to be explainable because anomaly detection methods applied in social settings need to be transparent to prevent any bias, for example racial bias. Secondly, anomaly detection systems must be robust because anomalous events could potentially be dangerous, so the systems need a solid guarantee of performance. Prior works have major shortcomings in both of these areas. Majority of the methods are based on complex, deep neural network-based pipelines and hence cannot explain the reasons behind the decisions they make. The ones that explain anomalies are brittle because they use off-the-shelf object detectors as a pre-processing step and fail to detect and explain anomalies when object detection fails. We address these shortcomings in our approach, where we first train an autoencoder to predict the next frame given 5 previous input frames. We then use the total error in the per pixel prediction error map to output an anomaly detection score. We also input the saliency map together with the real next frame to the explainability module to provide explanations of the saliency map and anomalies it detected. We can alternatively train the autoencoder for single frame reconstruction and use exactly the same pipeline. With this method, anomaly detection does not require object detection as a pre-processing step, giving robustness to object detected failures. To provide explainability to this robust method, we come up with a novel explainability module and we further improve the performance guarantees by proposing a novel autoencoder architecture. Previous methods often use autoencoders trained on normal events to detect anomalies, assuming they will make an error in reconstruction or prediction when testing on anomalous events. We argue that this could not be the case if the autoencoder generalized well. We address this shortcoming of previous works by designing VQUnit. It is a modification to UNet where we replace each of the features in the autoencoder bottleneck with the closest entry from a codebook lent on normal data only. In testing, this restricts the features to only come from a set of normal features. As a result, the decoder can only produce normal events, removing anomalous events, producing a prediction error which can be used to detect anomalies. As a result, VQUnit gives a better guarantee of performance than baseline autoencoders because the input to the decoder is guaranteed to be formed of normal features only. Another benefit is improved saliency maps. We then use the per pixel prediction error saliency maps from VQUnit to generate anomaly explanations. To do so, we run off-the-shelf detectors on the ground truth next frame, obtaining a set of bounding boxes and associated object and action labels. We then compute the error in the saliency map within each bounding box location given by the detectors. After thresholding the per box error, we use the labels associated with these boxes to explain the anomalies. Here we show example reconstructions of anomalous events where we train VQUnit for single frame reconstruction. When the input contains anomalous objects, baseline unit produces blurry version of the input, but the truck, bicycles, and person bending over are still clearly visible. Our VQUnit completely removes the anomalous events. In the case of the truck, it is replaced with person-like blobs. The cyclists are replaced with pedestrians, and the person picking up the bag is almost completely removed. This illustrates that VQUnit introduces a strong restriction on reconstructions. As you can see in these examples, we can successfully explain anomalies due to riding a skateboard, riding a bicycle, a truck, someone practicing martial arts, and someone picking up a bag. On the task of anomaly detection, we perform on par or better than other methods that provide justifications of their decisions. They are, however, less robust than our method due to the pre-processing with object detectors, and we outperform them on the task of anomaly explanation. Thank you for listening.